Good day, and thank you all for joining me on this webinar that we'll run through called Flow Through Structures. My name's Peter Coombs and I'm working on my own today, so if you have any questions, do feel free to put them into the message box, but I'll be running a demonstration live. So what I'll have to do is actually send out responses for the frequently asked questions that we get during the course of the webinar in the little pop-up box that you see on your screen. So welcome any participation and queries that you may have or suggestions for future webinars. So welcome for all those new attendees. As you'll see, there's a little pop-up box, and you can sit around and share this information with your colleagues, post questions to us, and as I mentioned, we will answer them in due course. So the subject of the webinar today is flow through structures, and what we plan to do, or what I plan to do, is to introduce how we can achieve more realistic simulations using the flow through structure process. I will demonstrate the new technology that we have in the latest version of MicroDrainage, which is the MDSuDS module, and look at how to design a range of different drainage structures. Following on from the previous webinar, there are three particular structures that were highlighted that people wanted me to sort of show them, so I've incorporated those into a model, and I'll just go through a brief process live with the software. And having designed them and tested them within the MDSuDS module to make sure that everything's working okay, I can then show you how to transfer those into an integrated MicroDrainage network model that will then provide you with an integrated sustainable drainage as well as a traditional drainage network, all combined in the one model. The driver for this has really come out of the new SuDS manual, Series C753. So we'll take a look at some of those elements. The four key pillars, for those that weren't in the webinar last time, we're looking at the water quantity, but satisfying the need for looking at water quality to comply with the EU Water Framework Directive, which also encourages us to provide better amenity and improve our ecosystems with improved biodiversity as well. So I'll run through with those four pillars in mind. So remember, these as the four pillars: quantity, quality, amenity, and biodiversity. The structures that people would like us to take a look at are things like swales, for example. Now, this is covered in chapter 17 of the SuDS manual. What we do with the swales, we design them with a width to convey fairly shallow flows within that vegetated zone. So if it's grass in the base, then 150 millimeters typically, for the regular return periods of like a 1 year, 2 year, 5 year return period. So this is just to convey the flow. The base of the swales are typically going to be between 0.5 meter wide up to 2 meters wide at their base, and the longitudinal slope along the length of the swale should be constrained to 0.5 to 6%. What we don't want is to have steep sloping sites with scour in the base. So these can be limited in terms of topography, but there are workarounds to that I'll share with you in a second. The side slopes of the swale should be ideally 104 or flatter if possible, but I do appreciate the land take situation, so it just depends on what we can fit in. The depth of them from the base up to the ground level would typically be about 0.4 to 0.6, so around about 0.5 meter deep is the norm. Not to say that these are hard and fast rules, but this is just like the best practice guidance that comes out of the SuDS manual. There are different types of swale. The one that you just saw the photograph of is the sort of top one, which is a grassy lined swale. Now, this could be used purely to convey the water for that 150 millimeter vegetative zone for the regular events, but then also to provide storage for the more extreme events. And then we can contain volume within the swale. They're very, very good at this. We'd have to have some kind of a freeboard, just to make sure the water doesn't overlap the top. So we'd like to have a freeboard value, a depth to which we're designing for the extreme events up to. The swales themselves could be in clay soils, so they can convey that flow, contain that volume for the extreme events. But if you're fortunate enough to have a free draining soil, then they could potentially infiltrate down through the base, even out through the sides as well. So that's a typical swale. The next one is a dry swale. This dry swale incorporates a stone trench with typically a perforated pipe in the bottom of it. So this has been advised in Scotland. They've had some very, very good experiences of putting in dry swales, particularly in Scotland. And this is probably the more normal way of doing things nowadays. And we could also put in a wet swale, so almost like a wetland, but in a swale kind of a format. So these are probably a little bit less common, but typically the dry swale and the swale itself would be the most common forms that we work with nowadays. They're really well suited for managing the runoff from roads and from car parking areas. We can incorporate them into landscaped areas and public open spaces, and they have excellent pollution removal characteristics. And we've put in their visibility because it was mentioned in the SuDS manual that if there is polluted runoff, it is clearly visible within the swale itself. You can literally see it. So it's not buried under the ground and piped away and passed downstream somewhere. They will be difficult to use in high, dense urban situations. They are a bit of a challenge if you have a steep sided slope, a topographical site with steep gradient across it. And we do need to be careful of infiltrating if we are taking diffuse pollution from, say, car parking areas, that we don't leach that contamination, if you like, down into the aquifer down below. So to that extent, we need to be mindful. Plus, you need to be careful of the groundwater table to make sure it is at least 1 meter below the base, not just of a swale, but of any infiltrating structure at all. But there's some really good examples to see within the SuDS manual, so I'd encourage you to get that and have a look. Where you do have steep sites, there are workarounds, as I mentioned. We'll look at some more shots in a minute, but we could put in larger stone riprap, gabions in the invert. This has been used successfully in some sites that I'm aware of to reduce the risk of that scour. The capacity is there to satisfy those regular events, the 1 year, the 2 year, the 5 year. We need to make sure that we're conveying safely those extreme rainfall events. So there'll be a question mark as to what we would need to convey for what's the definition of extreme. That could be 30-year with no flooding, for example, but then go beyond that and look at maybe the 100-year and add in for climate change. Now, if we do have flooding coming out of the swale, we then need to model that and manage the surface water, but the swale is a part of that surface water management process. The structure needs to half empty within 24 hours, such that if we have another rainfall event next day, that we've got sufficient capacity to handle that and for the no flood scenario to be carried on. The velocities, typically we'd like to keep them down to less than 0.3 meters per second to negate the risk of that scour. As I say, there are workarounds with putting in large stone, etc. And this is interesting, that the time of travel within the swale and the residence time within the swale itself, there are recommendations now coming through from the SuDS manual, and that is that we should have the water residing within the swale at least 9 minutes and sometimes up to 18 minutes, depending on the situation. And the roughness to use within the swale, I'd normally use 0.035 for a grassy swale scenario myself. That's extremely rough, but I need to just double check that and get back to you on that one. And we can use check dams to reduce the velocity. So along the length of the swale, we can put in some check dams to hold back and attenuate. If we're infiltrating into the ground, it helps to slow down that flow, contain it, and then allow the infiltration to take place. So it does increase the residence time naturally as well. And we also need to look at the nature in which the flow enters the swale. Typically, it'll be laterally across from the highway or across from the car park. There'll be lateral flow coming in. It's not necessarily point flow all arriving at the upstream end of the swale. In terms of amenity, There's some really good social studies that have taken place at sites like this one. This is Upton in Northamptonshire, and the photographs courtesy of actually, I think it'll be Northampton City Council, to be fair. And here's an example of a check dam that's been put in place to hold back and contain that volume. But the social studies have come back from all the residents, and they do find these particularly pleasing, aesthetically pleasing, and utilised as an amenity. When we're putting them in, we need to avoid putting in sort of 90-degree sharp bends in changes in direction. Better to put them in kind of meandering. If you put in sharp bends, we could get scour erosion on the outside of the bend because of the increased velocity of flow. And the planting that goes within the swale itself should suit the local situation. So do work with the landscape architect within the team to make sure that you're planting out appropriately. We can use them for educational purposes. At the Upton site a couple of years ago, we went there to launch some education boards, some interpretation boards that are around the site. The residents are really interested in these. They don't quite understand what they're doing. So to put in interpretation boards is really helpful and educating and engaging with the community. You can see here along the top of the swale that there's some little short posts and a fence just to make sure there's no vehicular parking going on or anything more dramatic than just a parking situation, to be fair. So there's a little barrier put up around the perimeter there to avoid anyone parking within the swale itself. The biodiversity benefits, they're all covered in Chapter 6 of the Syria manual, but often they are planted out with wildflower seed mixes, and this is providing a positive contribution to urban biodiversity. We're enhancing the ecosystem within the urban environment, and it creates a great habitat and also food for the insects and the invertebrates, etc. But we do need to use, again, indigenous species, so I take advice from the landscape architect in the team as well. We'll also take a look at pervious pavements. This is a popular choice because where we're restricted on high-density projects, you don't have the benefit of space to be able to put in a swale or a detention basin or something like this. But a permeable pavement, or pervious pavement rather, is a very efficient way to manage surface water, fit it into the densely urbanized situation, but also manage surface water very close to the source. It intercepts volume runoff and reduces volume, and provides water treatment as well. There are many forms of them. Look at the surface itself. We can have porous asphalt, we can have block pavers, we can have grass zoned areas. And the water, the runoff and rainfall will land upon the surface. It'll percolate through. There's a geotextile membrane here to ensure that there are no fines from the bedding of the paving, for example, migrating through into the structure itself, which is typically an open stone, like a 40mm nominal size, 30% porosity. This could be cellular storage as well. And the flow could either be attenuated within the stone and then taken away. So this could be in a clay soil, or if you, again, have a benefit of an infiltrating soil, it could infiltrate down into the ground beneath. Normally there's a perforated pipe that it is laid in the bedding material here as well, the stone material. So you can either infiltrate or maybe just attenuate. So they're very adaptable. Here's examples of some of the grass zoned areas courtesy of EPG. There's Lake Garda and up in Wales as well. So you can take the runoff from the impermeable area into the pervious surface, as well as taking the direct rainfall onto the pervious surface as well. The advice from the Syria guidance, and here are like more typical examples of the hard landscaped areas, so we can fit these in pretty well anywhere and everywhere, is that we should test these with a range of rainfall events to verify their performance. So I'll show you that in a second live with the software too. And finally, the third one that we'll take a look at in a little bit of detail are ponds themselves. They definitely satisfy the four pillars: the quantity, the quality, the amenity, and the biodiversity. We can utilize existing depressions in the ground. So if we interrogate the topography, find out where these low spots are, maybe we don't have to spend that much money to increase the depth of the depression, maybe build up a little bit of a berm or a bund around the hollows as well, and utilize those as surface storage. But they don't have to be like huge, massive ponds and lagoons. If you look at the example here on the right-hand side, a good example from Bob Bray, Robert Bray Associates in Gloucestershire, where there's a relatively small, hard landscaped planted pond here, taking runoff from a building, for example. So they don't have to be huge examples. And certainly in Sweden, in Malmo, they definitely like living with water within the hard landscaped environment. So you'll see these around the city of Malmo quite widely. So do think of those as being an option for you. When we design them, and I'm now thinking of the larger forms of pond, we need to design them so that the flow spreads out quite gradually. If we look at the larger pond on the upper example here, we need to be mindful as to where we put the inlet and we put the outlet from the pond. So if this was a fairly longitudinal lagoon, we wouldn't want the flow to come in here and then just shoot straight across the pond and then flow out on the other side. We're not utilizing the full benefit of retaining that water for at least a 24-hour period to get the silts and the pollutants to drop out and give that final polish, that final clean to the runoff before it discharges off-site. We'd like to put in a long, tortuous path to make sure that that happens. There are some good examples of putting underwater bunds, actually, to create continuous paths below the surface, actually, that are quite neat to be aware of. And the ponds themselves will help to reduce the peak flow rates as well. So what I'll do, I'll go over live and take a look at the software. I'll start off in MDSuDS, and I want to look at identifying the extent of the land take. This is probably one of the hottest topics about when we're working with sustainable drainage systems, and it really is all about, well, how much space do I have, how much land take, what will that structure take up? So we can look at designing some of those types of structures, and then understand how the water is flowing through the individual structure and then connecting from one to the other to create a complete SuDS treatment train. So we're going to look at how we create an integrated model within MDSuDS and then take those elements and then incorporate those into our network within MicroDrainage itself and look at a final test to make sure that we're meeting the pre and post development discharge type rates. So if I just go across to my MDSuDS, I just need to shut the window down for the GoToWebinar meeting. I'm not sure if everyone's been made aware of MDSuDS, but this is a brand new module that we have created. And we would like to have incorporated all the functionality that I'm about to show you within something like source control. But when you see what I'm about to do, you'll understand the reasons for why we can't just kind of do that. What I'd like to do is start off with this being a drawing board. And you'll see that there are a series of drop-down menus along the top of the screen. We have a tree view to the left-hand side of the screen and a toolbox to the right-hand side of the screen. I'm going to introduce you to some of these elements. So imagine this black area as being my drawing board. What I'd do to start off with is bring in my CAD drawing. So I'm right-clicking on the CAD data in the tree view, and I can load in a drawing. So in this case, I have a layout produced by an architect. If I say OK to that, the drawing's produced. If I have a layer of levels that are fairly accurate, then I could tick the surface data and incorporate a three-dimensional drawing to create a triangulated surface, a digital train model. This is just a flat 2D drawing, so I'm just going to bring that in and say OK. So now I have a layout. And that layout, if I move the mouse across it, you'll see that there are some eastings and some northings. So when I move the mouse over there are eastings and northings, but it's all at sort of zero datum. There's no information about the topography. So what I can do is I can bring in that information about the topography. Now at this stage, at the concept of a project, maybe I only have the land survey, or maybe the engineers have created a model for the highway layout, for example, and you can bring that in. Let's right-click on the surface option on the left-hand side tree view, and then load in data in terms of the surface. And you can see that we've got a range of formats that we could incorporate. just straight XL, CSV, XYZ columns, a CAD surface, XYZ, land XML, Esri's ASCII format. So if you've got LiDAR data, for example, from the PDS software PWF. So if you've got MX, you'd be working with probably land XML or Civil 3D. You can bring in from Civil 3D with land XML. And I've got a surface that I've already imported and created, which is our own XPSX format. So if I click on that and then double click, it's now populated the eastings and the northings along with those Z coordinates, the ground levels. And if I say OK to that, that information has now been incorporated because I noticed that the CAD drawings kind of shrunk. That means that the extent of the ground data is wider than the extent of the CAD drawing. So it's kind of created the effect to fit it onto the screen for me. And when I run the mouse over anywhere near the CAD drawing now and even beyond, you'll notice that there's a Z coordinate. When I come off the model, there are 0 levels, but when I move down across towards the drawing, you can see here I'm picking up ground levels because there's a terrain model beneath with the CAD drawing now draped upon it. What does that look like? Well, I can show you the triangulation. So that's why the screen kind of jumped. If I right click, I can band zoom in, and we can take a look at the layout of the site itself in a little bit more detail. Now, what would be useful at this minute in time is to switch off the triangles. I'm trying to orientate myself now. Where's the high ground? Where's the low ground? Where does the water want to flow? Based on the lasso guidance, really what I'd like to do is take, if I just pan back out, I'd like to take a look at where the outfalls for the site will be, or outfall or outfalls. We can click on the color fill. If I click on the color fill, I know the legend for this. I can click the legend on. So the higher levels are in red. So we're up at 49, nearly 50 meters above sea level in the red area to the northwest. And then green and yellow is going down towards the lower area. So basically, the water looks as though it's going to travel from the west, kind of southeast, I would say, across towards this side. So the outfalls are going to be over to the eastern side of the site, or outfall. It's just kind of helping us scoping out and start to picture what we would like to put in place. We can interrogate the CAD drawing and see what room we have to incorporate different things, and just help with this concept stage. If I turn the color fill off, the other thing I can do, I could deluge this with water and just see whether the water wants to flow across that surface. So if I right click on the deluge, hit green for go, can change the depth of water or the time of analysis. So let's see where 50 ml of water will travel in 30 minutes. It's easy enough to change the different parameters to check different scenarios and get a feel for where the water is wanting to run right now. And as we kind of suspected, if I right click and just pan in a little bit, there are a lot of arrows there, direction arrows now, showing us the direction of the flow of water across the surface. And then the color of the grid squares will tell me the depth of water. So it's fairly shallow. If I stop my mouse over here, the light blue is anything between 50 millimeters and 200 millimeters deep. So it's fairly shallow flow coming across the terrain. And then when we get across to the right-hand side, it's kind of ponding here. So the red area, this is up to 400 odd. This is 467 millimeters. If you look at the bottom of the screen, you'll see where my mouse is over the grid square is telling me not just the X, Y, Z coordinates, but also the depth of the water, the maximum depth of water that's traveled across that grid square, but also the maximum velocity of the flow of the water across the grid square in that 30-minute analysis period. So I'm already starting to get a nice sort of feel for the project that obviously our outfall would need to be across towards the right-hand side. And what we could do, if we turn off the deluge, it just switches off the imagery, so I still have the information, but it's switching off the imagery. And let's see, we've got some nice areas here where we could put in some porous car parks by the looks of it. I'm gonna give myself grace and say, oh look, I've got lots of space around here. Of course, I can feel you smiling, because I want to put in some swales around the perimeter. Maybe we can put in a pond for that final polish before discharging off to some form of watercourse or the public drainage system, and we can put some porous car park areas in place. So how do we go about this? Well, it depends on what's important to you at the minute. If it's space, what we could do is we could identify some drainage systems and put them in place, see how much space they take up, see if we can fit them in, and then take areas of runoff and put them into the storage structure to see if it's going to work. Let me, for example, drag over a swale. What I'll do now is I'll just define that swale. So let me say it's going to be this kind of a shape here. Make it a nice little shape like that. I'm just clicking to identify the extents of the swale itself, and right-clicking closes that. I could put one there. I could put maybe another one with an under drain. Bear in mind that the flow is going to generally come across towards the right-hand side here. So let me put in one with an under drain, so I have like two linking up with one another. Just left-clicking and then right-click, and it closes. It could be any shape or size. If I zoom in here, and if there's anything that I'm not particularly happy about, I can select and I can move that point around, make it a nicer shape if I wanted to, etc., etc. So I've got a couple defined there. Maybe I'll put in a porous car park over here, and I'll say, okay, let's put a porous car park. I'm doing this very quickly just for the purpose of the demo, but let's put a zone of porous car park in the middle, and then we might want to put in a pond, and that pond, I want to put that in as a nice kind of kidney shape for that long tortuous path that I was mentioning about. So ideally what I'd like to do is have inflow coming in at the upstream end here, a nice flow path along the length of the pond, and then an outfall at the downstream end. So we've identified the extents of the structures. If I double click on the swale, for example, this is to really show you the power of the MDSuDS and why we had to write this kind of from scratch to satisfy the latest guidance. What the program's done now, it's taken those clicks and the extent of the perimeter of the swale, and it's identified what the exceedance level is. So in other words, it's picked up the lowest ground level around the perimeter of the swale. So when the water reaches 34.13 meters, anything above that, it'll be flooding onto the surface, onto the terrain. We can put in a freeboard. So I would say, well, for a swale, let me put in a freeboard 100 millimeters below the natural ground level. You can see the length and the width, the base width of the swale shown here. If I click on the image below, this is basically what I've put in place. So I've identified the base width here, and the slope is the longitudinal slope along here. So maybe you want to keep it in flat or put it in very, very flat to make sure that there's no scour. I'll leave it at 0. What about the base level? So we've got here exceedance level 34.13. So 34.13 is the sort of top of bank at the lowest point. I want to put in the swale typically about a half a meter deep is what we're kind of recommending, isn't it? So that'll be 33.63. So 33.63 would give us a 500 millimeter depth of swale. So now we're down to the base level here again. And then the side slopes. Well, ideally we want to be putting in, 1 in 4 flatter if possible. And what this is now indicating to me is that we've got the base width, the widest base width is just over 15 meters. And then when I move over here, based on that 1 in 4 side slope on both sides, we're talking about a 20 meter top width. So this is why I say this is to help you to scope out how much space you want to put in here. So we can manipulate, we could cut down the base width and say, well, I just want it to be that kind of 2 meters. And if it's 2 meters wide with 1 in 4 side slopes, half a meter deep, then it's going to be 6 meters wide. You see where I'm kind of coming from. It gives you the flexibility to be able to look at such things. We've got some examples of the swales themselves. And here's the one with the meander that I had in my mind when I said it's nice to put them in meandering rather than straight if you do have the space, rather than just a straight run. But they are great alongside the highways typically, where they are normally in a straight long run. If they're not planted out, often you find that they will naturally vegetate with bulrushes and things like that, which will help with the cleansing, water quality side of things, as well as the biodiversity. And here's your typical example where runoff coming from the highway ideally across the grassy strip, filter strip, to then get into the swell would be the ideal way to go with this one, rather than having gullies and what have you with point inflow. So this is a sort of ideal situation where you can have lateral flow coming in constantly as you go down along the highway. And then there's the example from the Upton site in Northamptonshire, where we have these check dams to hold back the volume for the extreme events. So the regular events are conveyed through at the low level. Here are the naturalized bulrushes, and then you have a little slot here to maybe hold back for the 30-year return period or the 100-year return period when it weirs over the top. We've got advanced capability as well. So if you do have the opportunity to infiltrate through the base or through the sides, we could introduce that infiltration here. On this particular site, it's clay, so we don't have that luxury, I'm afraid. We could put in evapotranspiration figures, typically 3 millimeters per day. In the UK, a little bit higher. When you get over to the Middle East, it'll be like 11 millimeters per day. And the delay time. So this is that sort of retention within the swale structure at the surface. We can put in a delay time of that 9 minutes, which is 540 seconds. So the runoff will get into the swale. It'll be retained for 9 minutes before it's allowed to discharge out. So we're helping to provide that best practice analysis within the program. And then you can have a trench or not, as the case may be. That is the case with the next one. We can also add in pollution characteristics. We're not going to have time in the webinar today, but we could do a whole webinar just on pollution side of things, and that's pollution that's being taken out through the swale itself on the surface. And if we did put in a trench underneath, how the trench would also help to remove pollutants as well. So we could put in background concentrations of a range of pollutants, and then we can show how they're being removed, what the percentage removal is, and the actual reduction in concentrations of those pollutants. So I'm not going to save those changes, just want to show you how we go about it. How do we generate the runoff that's getting into the swale? Well, that would be an inflow, wouldn't it? So if I click on the inflows option down the right-hand side, that inflow could come from a roof, it could come from a hydrograph, if you know that information already, predetermined, or a green roof, or just an area. So let me say, look, there's an area here, and it might be this extent there that's getting into the swale. So now we can identify how the runoff from this area, where that flows to. Does it flow into the first swale or to the swale with the underdrain? We can start adding in inlet conditions. So when we do have flow entering into the swale, is it just point inflow? Well, we don't want that. We ideally want to put lateral flow going into the swale. So I've now added in lateral flow into the swale. And how does it get in from this area? We just need to connect the area to the lateral flow. So if I look at the connections, what do I want to do with that flow? Do I want to attenuate the flow on the surface before releasing it into the swale? Do I build in some kind of a lag time if we know what that is? Worst case scenario would be to have no delay at all. The runoff would land on this area and then laterally flow into the swale. That'd be like the worst case scenario. So if I go for the no delay, and I can just then connect the area to the lateral inflow of the swale. I hope you can sort of understand the power of what you can now achieve here. I could have made that a pipe, by the way, or any kind of form of channel as well. So now we've got runoff coming from an area, laterally flowing into the swale. The swale's got some characteristics to it, and then it's going to convey the flow to its lowest point and then get away. So what we can then do is have an outlet condition. So that outlet, maybe it's one of those check dams that I just showed you the photograph of, from one swale into the other that happens to have an under drain. So that would be like a weir. So I drag and drop a weir on here, and then you can set up the characteristic of the weir. So we can put in the width of the weir, the level of the weir, etc. To set these things up is kind of neat, because what we can do is we can have the window for the flow control, but then double click on the window for the structure itself. So the invert or crest level of the weir should be the invert of the base level of the swale. And I wiped out those results earlier on, so I don't have the level in there, but I take the level here. I could copy it and paste it into my crest level here, and then calculate the weir width. So then I'd have this runoff coming down into the swale, through into this swale, which itself could have another area of runoff entering into it, maybe laterally, plus the flow from the weir across into the swale. So I just add more connections in, and that could be, again, like no delay from the weir across into that particular structure. We can add in another area here, and so on and so forth. If I go over to the car parking area, let me just select that. You can see that we have the exceedance level again. So from the DTM, the program's identified the low spot around the perimeter of that car park at 36.74. So maybe we want to put the invert level in about 600 or 700 millimeters below that. Typically, we have about 200 millimeters. If I click up on the images here, typically the layer, the running surface layer is about 200 millimeters depth here, and then the stone underneath can be 400, 500, 600 millimeters deep, with or without an under drain, a perforated pipe. So we can tick that on, and then identify what the diameter of the pipe is, the depth of the invert level of the pipe above the invert level of the structure. So if you wanted to have 150 millimeters of bedding, for example, you could set all this up. The paving layer depth, as I mentioned, is typically 200 millimeters. What's the membrane percolation characteristics? Where we're cutting out the fines migration through into the stone structure underneath. We need to put those characteristics into the model. And the porosity of the stone beneath. If it's cellular storage, it would be 90%. If it was clean washed A40 stone, it would be 30%. And that's what I'm sort of putting in here. The length and the width have been identified by the program itself. And again, we have advanced characteristics. So I'm being able to put in evapotranspiration of about 3 millimeters a day. And again, we could put in a delay time if we know what that is. I couldn't see any recommendation on Pervious Pavements within the SuDS manual, but certainly the delay within the Swale was 9 to 18 minutes. And don't want to say that. I've got one in true Blue Peter fashion to show you what I've done earlier. And then we can set up our pond situation here as well, with freeboard and the base level and the shape and size of the pond itself. Once we've put in the information about each of the structures, you'll notice that we've got a volume shown at the bottom here. So you'll be able to work out whether your volumes are adding up in accordance with the quick storage estimate that you should have done in the first instance. So just to show you in the design tools, what we would do is put in, once we've characterized all the areas entering into the structures, we know what the impervious runoff will be, and we can calculate what the volume of storage will be required based on greenfield discharge rates. So the quick storage estimate calculator is within MDSuDS, and also the rural runoff calculator is also within MDSuDS. So you can calculate the greenfield discharge rates and then find out what the volume required within the storage structures would need to be. We can design the structures, make sure that the volumes are all good, and then we complete the model. So if I just go onto my Blue Peter. So here we are. This is the one that I've done earlier, where I've tidied up the swales and the pond. I've added in another couple of swales here and the porous car park area. So how are they all communicating with one another? Well, they're connected up. So if I click on the connections, you can see that holistically I've put this together. There's no pipe network per se yet. I just want to put together my ideas, my scenarios, make sure this is all working okay, run the analysis, make sure there's no flooding. And when I'm happy with that, then I can take these different elements and incorporate those into my integrated drainage network within MicroDrainage. So what I'm showing here are the connections that are in place. So here they're all set up basically. We can see long sections by looking at the profiles and create flow paths, so you'll be able to see the long sections, make sure all the levels are okay and things like that. They're all connected up, but where does the flow come from? From these areas. So I've just clicked the areas of inflow on the left-hand side to make sure we've taken into account all of the extent of the runoff areas. How does that runoff get into the structure? If I turn off the areas, there are inlets. So you can see the inlets have been switched on, whether they're lateral flows or point inflow coming in from the car park with the perforated pipe. We have a volume available beneath the permeable paving, and then there's a pipe coming across, and there's a point inflow coming into the pond from the car park. We have flows coming in from the swales to the west and from the north as well, all entering into the pond. And what about the outlets finally? So we have a range of weirs, orifices, pipes, depth flow relationships, whatever kind of flow control that you have. We've built that into the model here. So having created that model with my different elements, what I then did was analyze. So I've analyzed the system, so we can then take a look at the results. And I've run the 30-year return period and all the different storm durations. I've clicked on a little arrow at the bottom of the screen, so all the storm durations from 15 minutes up to 7 days, summer and winter. And this is now telling me on an individual storm by storm basis how each of those different structures are performing, whether they're okay, flood risk, etc., etc. I can move that over to one side and then look at a summary of all the storms, but then check for each individual structure. So in this case, our swell at the top end there, swell number 1, we've got flood risk, so the water's getting close to the surface but not flooding for the 30-year return period. And you have all the other structures in there as well, so you can just integrate, take a look and make sure that everything's working okay, which I know it is. So having satisfied myself that that's all doing a fine job, I can now move across into my drainage network. And this is now in MicroDrainage network. So I've put in the flow conveyance system. There's a little bit more information in here than in the previous. If I switch off the CAD drawing, you've got the traditional drainage system. I've incorporated some Gatic slot drain up here, by the way. That's a new feature that we have. So in terms of adding in proprietary sections, you can now add in Gatic slot drains for car parking areas to take that channel flow across, for example. But with my little toolbox, notice that we have the flow through structures option. And what I would do, when you're designing, by the way, just a word to the wise, when you're designing your network with draw nets in MicroDrainage, I would, having worked in MDSuDS, had an idea that I'd be putting in these swales and what have you. So I'd put swales in automatically within the model and then put in the flow through structure swale onto the swale location. It kind of works better because you've put the swale in at the surface within the model in MicroDrainage. It'll marry up nicer. Not a drama if you don't, but you'll be prompted for levels and things like that. So looking at the flow through structures, what I want to do now is add the swale in place. So if I drag and drop my swale, and notice that I'm dropping it onto that. I've actually put a pipe in the model rather than a swale. So I'm replacing the pipe with a flow through structure swale. And to do that, I just need to click on the import. And to do that, I need to go to my file, which is flow through structures. And it's not a source control file, it's a flow through structure. So it's in the MDSuDS file format of MDSX. And in my relevant file, here are all the different elements that I've designed in the one that I showed you, the completed one, the Blue Peter just now. And it's Swale 1 that I want to import. So if I say OK to that, it now brings in all of my information about that swale, add in the mannings then. Still not 100% convinced about the 0.35 mannings. I'm putting in the 0.035 for the grass. Say OK, and my pipe has now been replaced with the swale. I can do a similar thing downstream, and I can import. Just need to go to my file browser and then pick up the swale number 2 with the under drain. And again, I'll just put in a mannings N and then OK to that. Now, how about the ponds? So we're replacing all of these traditional drainage systems with the flow through structures. When we come down towards the pond, I've already got a flow control in place down at this location. But one of the main reasons why people wanted the flow through structures is also to better represent the model. So where everything kind of had to come down to, with a pond, a manhole, we had to drop a pond onto a manhole location. That's no longer the case. So I'm going to now take the pond, tank or pond option, and replace the pipe. So pipe 1005 is now going to be a pond that I've designed in MDSuDS. So I shall now import, using my browser, flow through structures, the MDS file for my pond. Okay to that. Need to put in even need to put in a mannings N for the pond itself. So you can see all these elements building up in the window. To take a look at those, you just look at the network drop down and your pond tank storage structure browser. I can replace those 2 swales up here as well. I'll do the Blue Peter and show you the one that I've already completed just because of the pressure of the time. But, oh yeah, the porous, let me show you the porous car park because there's a tip here I want to share with you. What I've done here, I've put in the drainage network around the perimeter. Now, what I recommend you do is is have something going through the middle of where you intend to put your storage structure. And I'll show you the reason for why in a second. If I drag and drop my flow through structure, notice I haven't got any pipes in the middle here. I'm going to have to put it on pipe 4001. And let me import that car park for you, which is here for us paving. Okay. So now we've got about 4 different elements in the model. When I show you this in 3D, it's going to put the car park so equidistant either side of that pipe. If we have a look at the finished model, I'll show you what that looks like. And I've run the analysis to check it. So here's it's the same model, but I just completed it. We've got the 2 swales here, 2 swales here, feeding into the pond, and then I've got the porous car park that's replaced pipe 4.001. But when we take a look at this in like a 3D view, and if I take away the horizontal compression there and then zoom in a little bit, you'll see what I mean about the car park. If I had a pipe running through the middle, either this way or this way, and if I dragged and dropped the car park onto the model there, it would have located it more realistically, basically. So you can now see that we have swale, a couple of swales coming down, having replaced the pipes, the porous car park coming down into the pond area. And what I've done, I've run the analysis so that we've now got the results. So if I take a look at the results, I've run the Discharge Wizard. So to run that, basically you hit the wizards, Discharge Wizard, and then you run through step by step. So we're running summer and winter profile storms, all the storm durations, 15 minutes to 7 days. I've run the 1, the 30, the 100-year return period, plus 40% for climate change. This is like the new recommendations coming out from the EA climate change guidance document. And then I've put in the 1-year return period. Bearing in mind I'm in clay soils, I know that we're going to fail the volume. I'm pretty sure that we're going to fail the volume post-development runoff compared to the pre-development runoff volume for the 100-year 6-hour event. So I've put in the 1-year peak discharge rate and the Q bar for everything above the 1 year. So in other words, for the 30 and the 100 year. And I've calculated the volume of pre-development greenfield runoff, and I'm going to get the program to run the minimal test, the minimal discharge test for the first 5 mil of rainfall to see what the most heavily polluted water runoff will be. So if I cancel that, I can show you the results because I've already run them. And you can see that we've got 1 green pass and then 2 fails. So the pass is the discharge rate. So we're hitting the 1-year discharge rate, just under the 1-year discharge rate, and then under the Q bar figure for everything above the 1 year. So we're okay in terms of peak discharge downstream of the pond. The volume, we've got a greater volume post-development than we have greenfield volume. This is typical with a clay soil. So that extra volume we need to put into long-term storage. We need to contain that within this confines of the site on the surface, release it back slowly into the network at a rate of 2 liters per second per hectare. And the minimal discharge, it's generating 13.7 liters per second of flow. If you needed to know what to put in terms of a petrol interceptor or some kind of a cleansing device, that's the flow that you need to contend with for the first 5 millimeters of runoff landing on the rest of the site. That should be sufficient to enable you to put your submissions in and gain an approval. So I'm really running out of time at the minute. It's 5 to 1, so I'm just going to recap and thank you all for your attention. I will pick up the questions and we'll do a frequently asked question sheet, fact sheet, and dispatch that out to everybody post-event. I hope you can see the benefits of using flow-through structures so that we can reduce those peak runoff rates, potentially reduce the volume of runoff as well, but providing those 4 pillars, that's the quantity, the quality of the water, adding in amenity value, as well as improved ecosystems with the biodiversity. It's really great to look at retrofitting, because with retrofitting, you're very much space inhibited, but we could put in things like bioretention areas within the highway, for example, and digitize them on a CAD drawing. So it's super useful for retrofitting as well as new developments as well. Just looking ahead to next month, we've got a pretty packed month from the 30th of May, so next week actually. We've got colleagues over in Germany. There's an IFAT conference in Germany going on. So if you are tuned in from Germany, pop over and say hi to the guys. It'll be good to see you. We're there until the 3rd of June. On the 7th of June, there's a conference in Wales, in Cardiff. It's the annual Wales Flooding Conference that we'll be attending. There'll be a couple of colleagues from the office there, so pop in and say hi to the team. Not quite sure in my mind who's going to be there at this minute in time, so I can't mention who you'll see. When it gets to the middle of the month, we have XP Swim training. This is the flood modeling and the drainage modeling software side of things. So that's been run from the 14th to the 16th. Following week, we have 4 days of MicroDrainage training, courses A, B, C, and H. A and B being the design fundamentals, and B, simulation and storage design. So these are the most popular. C is the graphical design, advanced modeling and graphical design. H is auditing and checking a MicroDrainage submission. So we run these kind of every other event. A and B are run on a monthly basis due to the popularity. So if you haven't already, I think we're pretty well booked, but have a look on the website and see if you can book yourself a place if you need training. On the 30th of June, at the end of the month, I'll be at this particular event in London with my colleague Ludmila Fedeva. She's the product manager for XP Swim, and I'll be presenting a 15-minute presentation. We're platinum sponsors there, so it'd be great if you pop by and say hi. We're platinum sponsors along with our friends from Hydro International. So you'll have a good day at that particular conference if you can get there in London. And the next webinar will be on Wednesday, the 6th of July, because we've got a pretty packed June there, as you can see. And without further ado, once more, thank you all so much for your participation and engagement, and really look forward to seeing you either at the conferences, the training, or the next webinar in July. Take care.